In this course, we have formally proved some theoretical results. The proof technique that we have used most so far is structural induction. However, there are some cases in which structural induction falls a bit short of what we can do. So in this video, we're going to introduce a stronger technique, which is induction on the size of the derivation trees.
Let's try to motivate this technique by means of an example. So if you remember the video of on big step semantics, this semantics was deterministic. That means that if we have two derivations of the state of the same statement under the same initial state, then both must lead to the same final state. So let's try to prove this by using the proof technique we have been using in this course so far, which is structural induction. And in this case, it will be structural induction on the statement S that we have here. First of all, we have to distinguish cases depending on the structure of S. So here we have the base cases, here we have the inductive ones, and each of the latter we can assume that we have induction hypothesis on each sub-statement that we have here. But just for the sake of conciseness and not to make a very long video, in this video I'm going to leave out the case of assignment because it's going to be very similar to that of a skip, and also the case of the if then else because it's also very similar to the case of the sequence and also very similar to the case of while. So we start with the case of a skip, and here above we have the property that we want to prove. So in the case of a skip, we assume that we have a skip sigma, which leads to sigma prime. On the other side, we have that thing, but assuming that the statement is a skip, so skip from sigma to sigma second. In this first judgment, the only rule that we could have applied is the rule for a skip, which says that sigma and sigma prime have to be equal, and in this case we must also have been using the same rule, which forces sigma to be equal to sigma second. So we have on the one hand that sigma prime equals sigma, which is what we have here, and on the other hand, this means that sigma second equals to sigma. So what we have is sigma prime equals to sigma second. That is what we wanted to prove. The case for an assignment, it's very similar, and that is why it's omitted here. Now we move on to a more interesting case, which is the case of the sequence, and here we can assume the following induction hypothesis, one for each substatement. So the first hypothesis says that if we have two derivations for S1 under the same initial state, then the final states have to be the same, and the other is the same thing but for S2. Okay, so we want to prove this property above under the case in which S equals S1 followed by S2. So assume that we have two derivations, S1 semicolon S2 sigma leads to sigma prime, and here that we have S1 semicolon S2 sigma leads to sigma second. In both cases, I must have applied the rule sec, which is the only one that we have for sequences. So in the first case, this means that there's some intermediate state. Let's call it sigma 1, for example, that S1 from sigma leads to sigma 1, and S2 from sigma 1 leads to the sigma prime that we wanted to have here. And here in the right hand side, the derivation at the right hand side, we have the same rule. We must apply the same rule. S1 sigma leads to some intermediate state. Let's call it here S2, and S2 sigma 2 leads to sigma second. So if we look at those judgments, we have two derivations for S1 under the same initial state, sigma. So by induction hypothesis, this means that sigma 1 equals sigma 2, which are both the final states. So if we know that sigma 1 equals to sigma 2, then this allows us to rewrite, let's change the sigma 2 by sigma 1 here. Oops, sorry. Sigma 1 here and sigma 1 here. That is when whatever we had sigma 2, now we have sigma 1 because they are said to be equal. So now look here at those derivations. We have here S2 under sigma 1, and here again S2 under sigma 1. So again, by induction hypothesis, we are saying that both final states have to be the same. So basically we're saying that sigma prime has to be equals to sigma 2, sigma second. So that means that sigma primes equals to sigma seconds, which are the final states of both sequences, which is what we wanted to prove. Now let's move on to the case of while loops. This is the induction hypothesis, so we can assume that the property that we want to prove holds for the body of the loop, which is S1, right? So again, let's assume that we have a derivation of while b do S1 under sigma, which leads to sigma prime, and the same thing while b do S1 sigma, which leads to sigma second. Which rule has been applied in these cases? So, well, it depends on the condition B, whether it's true or false. Then what we have is, let's start assuming that the condition is false under the state sigma. This means that at both sides, both derivations, we have applied here the rule while f, and here the same while f. So this rule says that sigma prime equals sigma, and this rule says that sigma second equals sigma. So at the end we have sigma prime equals sigma second because both they are equal to sigma, and this is what we wanted to prove. Now let's focus on the case in which the condition of the while loop under state sigma is true, which is the interesting one. So in this case we have to apply the rule while t in both derivations. In the first one, it means that we have to execute the body of the loop under the state sigma, and we get some intermediate state, let's call it sigma 1, and from this state we have to execute the whole loop again until we reach to sigma prime. At the right hand side we'll have something very similar. We first execute S1 under sigma, and that means that there is an intermediate state, let's call it sigma 2, and from now on we have while b do S1 sigma 2, which leads to sigma second. Okay, now look at this judgment here. S1 sigma leads to sigma 1, and here S1 sigma leads to sigma 2. So we have the same statement S1, the same initial state, and the induction hypothesis says that we've got the same, the final states should be the same. So at the end what we have is sigma 1 equals sigma 2. So let's clear this up a bit. So we have sigma 1 has to be equal to sigma 2, as we have said, and just let me replace here the sigma 2 by sigma 1 because both are equal. And now let's focus on this judgment and also on this judgment. We have the same statement, the same initial state. So one will say, well, let's apply the induction hypothesis so that sigma prime it's going to be equal to sigma second, and we are done. Well, that's wrong. The induction hypothesis refers to S1, which is a subcomponent of the while loop. But here we cannot apply the induction hypothesis to anything else. So it must be applied only when the statement is S1. But here we wanted to apply the induction hypothesis when the statement is the whole loop again. And structural induction does not allow us to apply the induction hypothesis here. So what can we do here? So instead of applying induction on the structure of the statement, we're going to talk about induction on the structure of the derivation tree. So if we clear this a bit, if you look at this derivation tree, here we have a tree that contains two subtrees. Now here is the first subtree, and here is the second subtree. Basically, the first subtree is the derivation of this judgment, and the second subtree is going to be the derivation of this judgment, which can be obtained by applying several rules. And the same here. We have two subtrees. This subtree corresponding to this derivation, this judgment, and the second subtree. If we use induction on the size of the derivation trees, then we can apply induction hypothesis on the subtrees instead of applying induction hypothesis on substatements. So more specifically, assume that you want to prove that a property holds for any judgment such as this one. So if you use induction on the size of the derivation trees, the base cases cover all those cases in which you have applied an axiom in order to obtain this judgment. So the rule that you have applied here could be a skip, it could be a sign, it could be the while in which the case is false, and so on. The induction step, on the contrary, is used in those cases in which this judgment has been obtained by means of a rule with several assumptions. So in this case, you assume that the thing that you want to prove holds for those judgments above. And then it's your job to prove the property for the judgment below. So the induction hypothesis says that you can assume the property for each child in the derivation tree, and then, assuming this, you have to prove the property for the whole tree. Now let's go back to our previous proof. But now we prove it by induction on the size of this derivation, this one. So let's concentrate on the case of while, which was a tricky one. The case in which the condition is false is the same as before. So now let's study the case in which the condition is true. So we know that there exist both derivations for some sigma 1 and sigma 2, which are the intermediate states in each derivation. Now we know, since the derivation tree of this judgment is smaller than the whole derivation tree, is a subtree, then we can apply induction hypothesis to prove that sigma 1 equals sigma 2. So this is what we get. Therefore, we can replace here sigma 2 by sigma 1. And again, now we have here the property that we want to prove, the same statement, the same initial state, but now it's going to apply it to a judgment which is whose derivation is a child of the root derivation that we want to on which we want to prove our property. So we assume that the property holds for those judgments, and we get what we wanted to get, is that sigma prime equals to sigma second, which is what we wanted to prove. So before we finish, let me highlight once more the difference with respect to structural induction. When we use structural induction, we could apply the induction hypothesis here, because S1 is a subcomponent of while B do S1. But we couldn't apply it here, because while B do S1 is not a subcomponent of while b do as 1, structurally speaking. So it's not a sub-statement of while b do as 1. So if we apply induction on the size of the derivation instead, then we can apply the induction hypothesis in both cases, because there's two derivations, trees, are subtrees of the whole tree. And this is what we need in this case.